In this tutorial, we will learn the basics of including the effects of solar radiation in BISTRA using the solar processor. This tutorial is limited to opaque materials. In the next tutorials, we will explain how to define glazing systems. We have already learnt to download the EPW file and link it to the functions window in the previous tutorial. We shall now further extend this by linking solar radiation data from the EPW file. At the functions window, we create a new function with the reference G01 for global radiation on a horizontal plane and then link it with the same EPW file that is for Brussels City. Then we create another function for diffuse radiation on a horizontal plane with reference code D01 and link it to the EPW file. We now click on the solar data icon at the top toolbar. Here we see the latitude and longitude for the location, which is read from the solar radiation functions G01 and D01, which in turn is linked to the EPW file. Next, we need to set the orientation of the bitmap. We need to give in the information for the bitmap if it is a horizontal section or vertical or inclined, and then, the orientation of the bitmap with respect to the north axis. For now, the bitmap is a horizontal section facing towards the south, which is also visualized from the sun path drawn at the preview. Here, the red line represents the x-axis, green represents the y-axis, and blue represents the z-axis. If we rotate the bitmap along the YZ plane around the x-axis with 90 degrees, we get a vertical section. If in case we rotate the bitmap along the XY plane around the z-axis with 90 degrees, we get the bitmap facing upwards, similar to a roof slab. You are also free to create inclinations along one or multiple axes. We changed this back to 0, which is a horizontal section. Then, we input the azimuth from the x-axis to the north direction as -90 degrees so the bitmap faces west orientation. We have defined the parameters for the sun in the solar data window, but have not yet activated it. Now to incorporate the effect of the sun, at the colors window for external boundary conditions with the color 170 toggle sun to yes to activate it. We need to define the solar properties of the materials facing the solar zone, which is decisive on how much it will heat up due to solar radiation. For each material, we have to define the solar reflection and the solar transmission. For the coating layer with color 57, transmission is 0, which means it's an opaque material. Reflection by default is set to 0.1, which means 90% of the solar radiation is absorbed. This would be a dark-colored surface. We first run a baseline analysis with a dark color coating. At the Edit menu, choose Report Definitions. Here, for color 57, which is the coating layer, we calculate the maximum temperature. Now we run the analysis by clicking on Calculate. Upon finishing, open Text Output and click on the Report Output tab. Here copy this data and paste it on a spreadsheet which will further be used to compare the results from this baseline. Now we change the surface reflection of the coating layer to 50% reflection, which would correspond to a light-colored surface. Here are some examples of solar reflection data for various colors. You can find this data specific to your project in the respective product manufacturer's datasheets. We now run the calculation. Upon finishing the calculation, open the text output and then click on the Report Output tab. Copy and paste this data into the spreadsheet for comparison. We generate a graph with the maximum temperatures for the coating layer with 90% and 50% solar absorption. Please note that for this example, we have used a global surface coefficient for the exterior boundary of 25 Watt per meter square Kelvin, which corresponds to a day with high wind speed. If we had chosen a lower surface coefficient, say 13 Watt per meter square Kelvin, corresponding to lower wind speeds, then higher surface temperatures can be expected. Click on the solar data icon from the top toolbar. Here, we see an option to change from the real sun path to a fixed sun position. Then, we can input the total radiation as a function I01 or a constant value. Then, we define the angle of incidence for the sun's position. We change it back to the real sun path to link sun position and radiation to weather data. Click on OK to close this window. In the next step, we will explore options to include solar obstacles in the model. We differentiate between an obstacle far away from the model, for example, a neighboring building or a tree, and an obstacle close to the model, for example, a shading device. For the first, an obstacle far away, we use the option Sun Obstacle. For the latter, an obstacle close to the model, we include that in the bitmap itself. Let's first explore the option to define an obstacle far away via a Sun Obstacle. Click on the Sun Obstacles icon from the top toolbar. A sun obstacle is a spherical rectangle defined by azimuth and altitude coordinates within which the sun is invisible. This can visually be seen in the solar data window. Here we see a gray zone indicating the default 5-degree shadow. Each sun obstacle is defined by 4 parameters: minimum and maximum azimuth, and minimum and maximum altitude. We can add a new row here by clicking on Insert After. Now say we define a nearby building via a sun obstacle with the azimuth ranging from 45 to 90 degrees and a maximum altitude of 60 degrees. We input this data at the Sun Obstacles window. Click on Solar Data to visualize the obstacle preview. This can also be visualized in graphic output. Now click on Sun Position and then click on Obstacles. In the shadow, the sun is gray, which is when it's behind the building. Then only diffused radiation falls on the model's surface. When it's yellow, we get direct radiation on the model's surface. In case of obstacles close to the analysis geometry, we can directly draw them on the bitmap. Say, for example, we wanted to create a louver shading element for the facade. We first delete the second sun obstacle. At the top toolbar, we have Draw Tool, Line Tool and Rectangle Tool to directly draw on the bitmap. We now extend the exterior boundary by increasing the width. From the bitmap menu choose Size. Currently, along the width there are 65 pixels, this is also seen in the Measures window. Say we want to add 40 more pixels along the left margin. We now get 105 pixels in total. Check Use Border Colors, so that the newly created pixels will have the same colors as the borders of the bitmap. Click on OK. Next, from the Colors menu choose List Defined. Here choose Color 8 representing aluminum. Now using the Rectangle tool, we create a shading of the louver fin. To visualize the impact of direct solar radiation on this bitmap, from the Calculation Parameters menu change the calculation start to day 160 and 9 hours. Click on Calculate to run the analysis. Upon completion, open the graphic output. Fill the bitmap preview with absorbed heat flux to visualize heat falling on the shading element. Fill with temperatures to visualize the effect of shading over the facade. Now we visualize the result for each time step. You now can close the graphic output window. Lastly, we can rotate the bitmap for it to be a vertical section for analysis. Click on Solar Data. Here we rotate the bitmap upward in the YZ plan around the x-axis. The elevation angle is set to 90 degrees. Click on OK and then click on Calculate Bitmap to visualize the result. Thank you for watching, see you in the next tutorial.